Let us start our 12th lecture. The topic we just continue where we have left in lecture 11. So, lecture 12 is basically how to determine the value of gamma SL and the physical concept of interfacial energy. Now, if we come back to this particular board, and you can see that in case of simple cubic, all the atoms are connected and 2r, this if this radius is r. So, you can see this lattice parameter which is A equal to 2r. So, the nearest neighbor is this, and at the same time if you see this, these atom if we consider, these atom is joined with 6 atoms. So, that means these 3 it is very clear. Now, there will be one more cube in front of this, there will be 3 cubes, and see it will be connected with. So, this is let us say this, and then there will be one more side here. So, this side. So, there this atom will be connected to another atom, and the back of that there will be one more lattice. So, that will be connected. So, you will see that the 6 atoms are connected to one atom. Now, at the same time if you see BCC, in case of BCC, this is the BCC, the nearest neighbor would be this one and this one. So, if we try to draw it, now this atom and then center atom and this corner atom. So, this is my body diagonal passing through the center of all 3 spheres, and then 3 spheres are connected each other. Okay. So, these 3 spheres are connected. 3 spheres are connected, and if we connect this, this is the length of the body diagonal. Okay. And it is bonded, this atom if we consider, this is center atom, it is bonded to this atom and this atom because these are the nearest atom bonding. Then this atom would be also bonded with this atom, this. So, this center atom will be bonding to all the corner atoms. So, that means the center atom has got 8 bonds, and these bonds are all the so there will be 8 bonds. So, these bonds will be all connected. Now, in case of simple cubic, so one atom is connected to 6 atom, that means bonded. So, that means 6. So, nearest neighbor number is 6. Then in case of BCC is 8. So, these are the nearest atoms and the bondings are taking place. So, but these atom and these atoms are not bonded. Now, in case of FCC, if we see this particular example, I can draw one more lattice, one more cube on top of this. So, that means this is one lattice, and this is, if you put atoms, it becomes crystal, and at the center point we have atoms. Now, in this case, the nearest neighbor would be this atom, this center atom of the face, the top face, and this atom. So, this is these 3 atoms are joined together. Similarly, the cornered atoms like this. So, this is the face diagonal, and there we have just like this, where the 3 atoms are joined together along the body diagonal. Here 3 atoms are joined together along the face diagonal. And if we try to see the nearest neighbor and the same distance, and here also if you see that it is the same distance, all those joined atoms are half of the body diagonal. And here the nearest neighbor atom position is half of the face diagonal, and these also connected to this center, the back of the face, this particular plane. This atom is basically situated at the center of this, the back of the plane. So, this is connected, this is side plane, this is connected, and then on in front this particular plane, the front plane, that means this particular plane, there will be center atom. So, this is connected to that. So, that means it is connected to all the corner atoms of a same phase, and then all the center atoms of the top unit cell, and similarly this will be connected to all the phase points, and then the back of the face there will be one more. So, this is connected. So, that suggests that there are, in case of FCC, 12 nearest neighbors. So, this 12 nearest neighbors, that means each atom there will be 12 bonds. This information is very critical. So, how many bonds will be there per atom? This is extremely important information. That is what we are getting into this crystal system, crystal structure of simple cubic and simple cubic, FCC and BCC. Now, in this case, this is another information which is critical, because in simple cubic we have seen that 2R is equal to A, which is the lattice parameter. In this case, it would be 4R, because these body diagonals are connected, all the spheres are connected. So, this is 4R. So, that means these are, this is 2R, this is R, would be equal to root 3 A. So, this body diagonal for a cube. Similarly, for FCC, 4R again, because if we try to see this atom, so this atom is connected to this particular center of this atom and this atom. So, this is 4R is equal to root 2A. So, A is nothing but the lattice parameter. So, this is another important information, because we need to have this information in order to calculate many other factors for those solids like density. We can get the value of density, that is the theoretical density, and then we can also get the value of this is one information which is very critical. Then another information which will be very critical is surface density. Surface density of atoms. In order to calculate surface density of atoms, we need to know the lattice parameter, at the same time the atomic arrangement of that particular surface. And then whenever we talk about the surface of this cube, we talk about the surface in the form of planes. And in case of cubes, the planes are dictated in the form of Miller indices. For example, we can have 1, 0, 0 plane, we can have 1, 1, 0 plane, we can have 1, 1, 1 plane, and there would be family of planes. For example, if I consider a simple cube, these are the plane notation. and these are Miller indices. So, we will not go detail how we get these values, but rather we simply denote what are those planes. Now, if we try to see a simple unit cell of FCC, let us say I would like to see the FCC unit cell, or let us say simple cubic. First, let us see simple cubic. This is a simple cubic, and these are, let us say, axis. This is C axis, which is Z, this is A, let us say this is B. And in order to find 1, 0, 0, and let us say these are all positive direction. So, 1, 0, 0 plane would be this plane. This is 1, 0, 0. Now, if we would like to find out 0, 1, 1, 0, 0, 1, so 0, 0, 1 would be this plane. Now, if we would like to find out 1, 1, 0, so 1, 1, 0 would be, so I would request you to go to some simple material science book and then textbook and get to know this plane and plane notation and other things. You can also find out open source available in internet, you can Google it. So, this is another plane which is 1, 1, 0. Similarly, we can have several such 1, 1 plane. This is another. So, this is another plane. So, this you can see that this 1, 1 plane and this 1, 1, this is 1, 1, 0. This is also a family of 1, 1, 0 plane. So, they are crossing at 90 degree. Now, we can have one more plane which is 1, 1, 1. So, that is, if I try to draw with yellow chalk. So, this is this yellow one is basically 1, 1, 1 plane. Now, depending on these planes, let us say I have a cube like this, and let us say I cut it and there is another cube on top of this. I remove the top cube, and then that means I am exposing 1, 0, 0, 1 plane. And when I am exposing 0, 0, 1 plane, I am actually breaking those bonds which are formed between the atom on the face of this particular plane and the 4 faces of the side faces of the top cube. So, those planes are out, those bonds are out, not planes, the bonds are out. So, that means those bonds I have cut it. So, if I cut those bonds, if I draw the top So, if I cut those bonds, this is forming the bonds with this plane. So, this bond is broken, this bond is broken, this bond is broken, this bond is broken. So, if I cut those bonds, I am cutting 4 bonds per atom out of 12 bonds, is not it? Because these atom is having bonds with 12 neighbor, and out of that 12 neighbor I am removing 4 neighbor of this atom, nearest neighbor I am removing. So, I am cutting this all this 4 bonds. Now, when I am cutting these 4 bonds, I have to calculate then how many bonds I am cutting over the entire plane.
Now, whenever I try to find out the number of bonds cut over the entire plane, I have to find out what is the number of atoms per plane. And whenever I am trying to find out what is the number of atoms per plane, I have to also find the area of that plane. So, per unit area of this plane, how many atoms are there? So, that information also will be required. So, another information. So, this is one information, this is second information, and third information is how many per plane. So, now once we get these informations, and of course, all three things will be using one common data, which is the bond energy. And each atom, each metal has got a specific bond energy. And for example, in case of copper, the bond energy we can find out it is 56.2 kilojoule per mole in case of copper. I think 56.2, I will just get to see the value and then again come back to this value, because we will calculate surface energy of copper of this 001 plane or a family of 100 plane. So, whenever we talk about family, this particular notation, the first brace is replaced with this brace. So, this is this becomes a family of planes. Now, once we have this 4 information, we would be able to calculate the surface energy. And we can also calculate if we know few other things. For example, if we know atomic weight of a metal, we can calculate density too. And this density would be required in order to calculate the molar volume. So, we are here one information, this Vm. This Vm can be calculated once we have the information about the lattice crystal structure, and once we have the information of atomic weight of that particular pure metal, we can definitely calculate Vm from the density information or the simple atomic weight and one more information, which is basically lattice parameter. Lattice parameter. Now, when we try to calculate let us say first let us do for example, let us say let us calculate density of copper. Now, copper is FCC and at the same time lattice parameter, which is A, is 3.61 angstrom. We can write it as 3.61 into 10 to the power minus 10 meter. And atomic weight is 63.55. Now, this is FCC, we have lattice parameter. So, we can find out how many atoms are there in a particular unit cube. And if you come back to this particular FCC crystal, you can see that there are 4 atoms at the corner of the lattice, 1 each at the center of the face. So, that means if we try to find out what is the number of atoms per unit cell, then it would become, so we can find out number of atoms per unit cell. So, then this cross I am just denoting as the atom. So, now number of atom would be, these atom will have 1/8 contribution to the unit cell. So, 1/8, and there are 8 corner atoms into 8 plus in the face it would be shared by 2 side by unit cell. So, the contribution of this atom would be half to 1 unit cell. So, half into 6 such atoms. So, it becomes 4. So, 4 atoms per unit cell. And now, this particular atomic weight information we can relate it to the Avogadro number, because it is a mole of copper. So, this gram is equal to 6.023 into 10 to the power 23 atoms. So, this is equivalent to these many atoms of copper. I know 4 is the atom per unit cell. So, then what would be the volume of this unit cell? The volume of unit cell, this is A, this is a cube. So, that means it would be, the volume would be A cube equal to 3.61 into 10 to the power minus 10 Q meter cube. So, that means 4 atom is occupying this much volume, and density is what? Density is weight divided by volume, or the mass divided by the volume. Now, this information we can use. So, that means these many atoms is equivalent to 63.55 gram. Now, at the same time 4 atoms are occupying this much volume, then 1 atom is occupying how much volume? So, I can calculate 1 atom is equal to 3.61 into 10 to the power minus 10. I can convert this meter cube to centimeter simply multiplied with 2. So, that times it becomes centimeter. So, I just put 8 centimeter cube divided by 4. So, 1 atom volume, the effective volume of the 1 atom would be this. Now, here I know this is the number of atoms. So, I just replace this volume of 1 atom 6.023 into 10 to the power 23 into 3.61 into 10 to the power minus 8 cube. So, that means this much would be the volume, which is equivalent to 63.55 gram. Then per volume, unit volume, the weight of the unit volume would be so if we calculate this, just wait, let me bring the calculator. So, 63.55 divided by 6.023 by 3. Oh, so I am missing one 4 term.
into 4, because that 4 term came from the 4 atoms are occupying the volume of the cube. It is coming about 8.97 gram per cc centimeter cube. So, this is the density of copper. Density of copper. So, we can calculate the density if we know how many atoms are there in an unit cell, if we know the lattice parameter. Similarly, we can also calculate the planar density. So, that means this plane we can calculate how many atoms are there per unit area over this plane. So, if we try to do that, so this is atom, this is atom, this is atom, this is atom. Now, over this particular area, we have over the area of A square, we have how many atoms? So, if we see on the plane surface, if we see, so this is another atom, this is mind it, these atoms are not joined, only these 3 are joined. Now, in this case, if we see the projection, 1/4 of this particular circle, if we project a sphere on a plane, it will become a circle. So, projection becomes 1/4. So, that means on A square you will find, and this becomes 1. So, 2 atoms. So, 2 atoms per in A square area. So, we can find out what is the density of that plane. So, or we can find out how many atoms would be there per unit area. So, we can find, so 1 atom is there. So, that means per unit area would be atom per unit area would be 2 divided by A square. If we calculate this, it would become 1.53 into 10 to the power 19. So, this will be required for our calculation of surface energy of the surface. So, now from this it is pretty clear that why we said that this 4 information would be required. So, one information is how many atoms per unit area of a plane. We have found that value for copper. If we replace this A by 3.61 angstrom, you will get that this is the number per meter square. So, that means per unit area these many atoms will be there over this plane. So, these number of atoms will be required, and also we also get to know that each atom we are cutting 4 bonds. So, we can, if we know these many are the atom number on this plane. So, this multiplied by 4, that many bonds will be broken out of 12 bonds per atom. Okay. So, we will need that information. We will do that calculation in our next calculation. What we have done, we have seen how to get to the information that enables us to find out surface energy. So, we have found out the last information, that is how many atoms per unit area of a plane. We on the way we have also calculated the density of copper, and next class we will find out the bond energy. We will take it from literature or the book, and then we will calculate how many bonds per atom, what is the bond energy per atom, and then its consequence on the surface energy evaluation. So, let us stop it here, and we will continue in our next lecture. Thank you very much.